This is my full adder circuit. This is the code for my full adder circuit. It is a 1-bit full adder, even though it may say 2. This is a 1-bit full adder circuit. And here in my design source code, I have input A, B, and carry in. Carry in is important because that is what makes it a full adder, is including that carry in portion. And we assign, or we have our outputs sum and carry out. And we have these declared in our full adder module. Now we want to assign the correct things. So we have sum is tied to A XNOR B XNOR carry in. And then we have carry out, which is designated to A and B, or carry in and A XNOR B. That's important for our program here. That's going to allow us to have this function run correctly. In order having this set up correctly right here, we're going to look over here at our simulation source, and it's a similar story where we have in our UUT we've called our inputs as A, B, and carry in. Those are our inputs, and our outputs are wires instead of reg. They are wires. And so our sum and carry out, those are our outputs. And then we go down here into our full adder UUT, where we connect these two. The output A is represented by the letter A, output B is represented by the letter B, and so on and so forth, or inputs and outputs. Now we begin running our simulation with the given values 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1. Alright, and let's run this and see what we get for our expected values of a 1-bit full adder. Okay. Now, for this one, we have 10 seconds as our step time, or 5 seconds rather, 5 seconds. So every 5 seconds we'll switch to a new values for our inputs and see what comes out. So here in the first 5 seconds we have 0, 0, and 0 for A, B, and carry in respectively. And of course that produces 0 and 0. We have 1 and 1 in A and B, and then 0 for C, and that produces 0, 1, or 2, which is good. That's what we expect. A is 1 plus C in, which is also 1. That gives us 2 again, which is correct. And then for our final one here, we have A, which is 1, B, which is 1, carry in, which is 1. So we're adding these 3 together, and we get sum and carry out as 3. It represents 3. And I would like to mention, I haven't already, but carry out is our most significant bit, and sum is our least significant bit for this adder. Now let's look at our elaborated design. And here we have our design. We can see that the XOR is tied to A and B, and that feeds into the AND of the carry in, and also that carry in feeds into the output of the XNOR over here, into this XNOR, which feeds into our sum bit, or least significant bit, and then our carry out is fed by this AND connected to our A and our B, as well as an XNOR, which is tied to the AND of the carry in and the XNOR of A and B.